On the left, you can see a form of carbon, and on the right, you will see another form of the same element, carbon. So on the left, you have diamond, and on the right, you have graphite. They're both different forms of the same element. How is it possible that the same element exists in two completely different looking forms? You'll find out in this video, so stay tuned. Assalamu alaikum everyone, this is Fahad Ansari and I'm here to help you conquer chemistry. Before we begin today's video, just a reminder once again that over 70% of you still haven't subscribed to my channel. So if you're one of those people, make sure you push the subscribe button, press the bell for notifications, and now let's begin. So today's topic is shapes of molecules, and these shapes are governed by a theory with a very weird sounding name, which is the VSEPR Theory. Now VSEPR stands for valence shell electron pair repulsion, right? So this is the fancy acronym that we're going to be using. Basically what this says is that different pairs of electrons repel each other by different amounts, right? So there are two types of electron pairs, in case you don't remember. There are lone pairs. These are electrons that belong to only one atom, whereas bond pairs are these shared pairs of electrons between two atoms that are bonded together in a covalent bond. So lone pairs and bond pairs repel each other differently. And the ranking of these repulsions is that two lone pairs repel each other the most, right? And the reason for this is that because a lone pair is attracted by only one nucleus, so it has a high negative charge density, and so it can repel other electrons more. Second electron pair repulsion intensity is between a lone pair and a bond. Basically, the electrons shared by two atoms in a bond. Electrons in a bond are attracted to two nuclei at the same time, so their negative charge density is a little lower, and so they are not able to repel other electrons that much. That is why two bonds, electrons in two separate bonds, are going to repel each other the least. And by the way, when we talk about lone pairs and bond pairs, we talk about the center atom, right? The center atom, when I use this term to describe shapes of molecules, the center atom is an atom that is bonded to at least two other atoms. So that is a center atom, right? So using this VSEPR theory, we're going to look at the different shapes of molecules and the different bond angles that allow the repulsion between electron pairs to be minimized and thus making a stable shape. So the first case is of carbon dioxide. Over here, the center atom is this guy over here. The carbon atom is bonded to two oxygen atoms, and we have two bonds around the center atom, one double bond over here and one double bond over here. So these two bonds are going to repel each other, right? And they're going to try to make sure that the distance between themselves is the maximum, so the repulsion is the minimum, right? So the maximum distance is achieved at a bond angle of 180 degrees, right? And so the shape of this molecule is called linear, right? So in summary, when you have two bonds on the center atom, in this case the carbon atom, and you have zero lone pairs on it, the two bonds are going to repel each other and settle for a linear shape at a bond angle of 180 degrees between the two bonds that are repelling each other. Now, this molecule over here is boron tribromide, BBr3. And over here, the boron atom in the center, this guy is the center atom. And it is bonded to three bromine atoms. So over here, you can see that the boron atom has 3 bonds around it and no lone pairs. So the 3 bonds are going to repel each other equally, right? So this bond is going to repel this bond just as much as it repels this third bond over here, right? So when these 3 bonds repel each other equally, they're going to settle at bond angles of 120 degrees apart from each other to minimize the repulsions. And so the shape of this molecule becomes trigonal planar, right? Basically, that's a fancy word for a flat triangle, right? Because if you connect the 3 corner atoms over here, these are the atoms other than the center atom, the corner atoms. If you connect them with straight lines, you get a flat triangle, right? So in summary, if you have 3 bonds, now notice I've changed the number of bonds over here. The number of lone pairs is the same, which is 0 on the center atom, right? This boron over here is your center atom. Then you have a trigonal planar shape with a bond angle of 120 degrees. Now we have an interesting case of methane, CH4, right? Now over here you might be thinking that we have 4 bonds, right? And no lone pairs around the center carbon atom over here. So you might be thinking, well, the repulsion will be minimized when these bonds are at a bond angle of 90 degrees apart from each other, but that's not the case. The reason is that these molecules are not restricted to 2 dimensions, right? Linear and trigonal planar molecules were 2-dimensional. They were flat. But this molecule actually has the option of moving about to 3 dimensions and increasing the bond angle so that the repulsion is further minimized. And that happens in a shape that looks like this. So you have the center atom over here, and you have these 2 carbon-hydrogen single bonds that are in the same plane as the screen. You have this carbon-hydrogen single bond over here that is coming out of the screen. This solid wedge is basically the convention of showing a bond coming out of the screen, right? So this is out of the screen towards you, the viewer. And this bond over here, this carbon-hydrogen bond, this dotted wedge, shows that this bond is going away from you, the viewer, into the screen. So the bond angle over here is a little greater than 90 degrees to minimize the repulsion and maximize the stability of the molecule. And this is actually going to be 109.5 degrees. And so when you increase the number of bonds around the center atom from 3 to 4, and you have 0 lone pairs, still the shape will change to tetrahedral. And notice that the bond angle is decreasing when you increase the number of bonds while keeping the lone pairs constant. First you had 2 bonds, that was 180 degrees. Then you had 3 bonds, that was 120. And now for 4 bonds, you have 109.5 degrees, right? Now this tetrahedral, basically, this literally means 4 triangles, right? And how are these 4 triangles? Well, if you connect the 3 hydrogen atoms that I'm circling right now at the bottom with a triangle, and then you make a triangle stand on each of the edges of that triangle that I just drew, one over here, one over here, and one over here. And these 3 triangles that are standing up on these edges, they meet at a common vertex, which is this hydrogen atom. You get 4 triangles that are equally sized, right? So that gives us the tetrahedral shape. So coming back to our question at the beginning of the video regarding diamond and graphite, how are they so different when they are the same element, which is carbon? Well, the reason is that diamond has a structure like this. You have each carbon atom represented by this dot over here that is bonded to 1, 2, 3, 4 other carbon atoms. So over here you will have 4 bonds and 0 lone pairs. So that will give us a tetrahedral shape that we just saw. And this will be a 3-dimensional crystalline shape of diamond that we know of. Whereas for graphite, each carbon atom is actually bonded not to 4 other atoms, but to 1, 2, 3 other atoms, right? So over here we have 3 bonds, and again we have no lone pairs because this is carbon, and this will give us a trigonal planar shape. And as a result, we have flat molecules, not 3-dimensional, these are flat 2-dimensional molecules, and that gives us the shape of graphite, which exists as solid black layers that rub off each other, and that's why it's used in your pencils. So that is why diamond and graphite look so different, even though they are essentially the same element. Now on to the next shape. Now what we're going to do is we're going to change the number of bonds and lone pairs, but we're going to keep the total number constant, right? So previously we had 4 bonds and no lone pairs, that was tetrahedral, right? Now we're going to decrease the number of bonds to 3, and the number of lone pairs will be increased to 1. So over here you can see I have changed the number of bonds to 3 and the number of lone pairs to 1. Now what happens as a result is this lone pair is going to repel these bond pairs away from itself more than the bonds repel each other. So as a result, the bond angle is reduced from 109.5 in tetrahedral to 107 degrees, right? That basically means that the bonds have been forced closer together because of the presence of this lone pair that has a greater repulsion strength. And so we have this shape, which is trigonal pyramidal, right? And this can be achieved by connecting the hydrogen atoms over here in a triangle. So you have a triangular base, and if you make a triangle stand on each of the edges of this base, one over here, one over here, and one over here, you can make them meet at the nitrogen atom over here. And so this will give us a trigonal pyramidal shape. So it's kind of like tetrahedral. The only difference is that you can consider this to be a squashed version of a tetrahedron, right? So that is the shape. And over here, what I'm doing is I'm replacing 1 lone pair with 2 and 3 bonds with 2. So I have decreased the number of bonds and increased the number of lone pairs. And so these 2 lone pairs are going to repel each other the most, right? Followed by the repulsion between the 2 lone pairs and each bond pair. And then these 2 bonds are going to be forced so much closer together that the bond angle is even smaller than 107. It's going to be 104.5 degrees, right? And so the shape is going to be called bent or V-shaped or nonlinear. These are 3 different names for the same molecular shape. So now we have 2 further shapes, 2 special shapes to consider. Over here we have phosphorus pentachloride, PCl5. And over here this basically consists of 5 bonds and no lone pairs. Because phosphorus is in group 15, it has 5 valence electrons, right? And they are all used up in the bonds. And so there are no lone pairs over here. And so as a result, they will repel each other equally. And basically what happens is this, and this chlorine atom, they're going to repel each other in the same plane at bond angle of 120 degrees, right? So we're going to have a 120 degree bond angle over here. So these 3 chlorine atoms are going to form a flat triangle, right? Then what we're going to do is going to make 3 triangles stand on each of the edges, one over here, one over here, and one over here. And so they're going to meet at this chlorine atom. This will be the common vertex. And so we will have 3 triangles up here that are meeting at this vertex. And similarly, we will have 3 triangles, one on each edge of that flat triangle in the middle. And this will be the common vertex, the bottom chlorine atom. And so you will have 2 trigonal pyramids sharing the same flat base that I'm circling right now. And so as a result, the shape is going to be called trigonal bipyramidal, right? So you have bond angles of 120 degrees within that flat triangular base that both pyramids share. And the bond angle of 90 degrees that you see over here is actually between the top chlorine atom over here and the triangular base, and the bottom chlorine atom and the triangular base in the middle that both pyramids share. So that is trigonal bipyramidal, from 5 bonds and 0 lone pairs. And finally, we have sulfur hexafluoride, SF6. And over here, basically, we have 6 bonds and 0 lone pairs, because sulfur has 6 valence electrons. It's in group 16. So this is 6 bonds and 0 lone pairs. And so they repel each other equally. And so the shape turns out to be octahedral, right? With bond angles of 90 degrees throughout. And over here, you can see that these two SF bonds over here are going out of the screen towards you, and these 2 bonds over here are going into the screen away from you. So these 4 fluorine atoms can be connected together to form a square, right? They can form a square, and this is a square base that 2 shapes are going to share, right? 2 tetrahedrons are going to share, in fact, because you're going to have 4 triangles, 1 on each edge, 1 here, 1 here, 1 here, and 1 over here, that are going to stand up and meet the vertex, which is the top fluorine atom over here. And you're going to do the same for the bottom fluorine atom. So 4 triangles at the top and 4 at the bottom. So 4 plus 4 gives us octa, which is 8, and hedral, which is triangles, right? So 2 tetrahedrons sharing the same square base, it's going to be octahedral, right? So these are the shapes of molecules that are part of the AS level chemistry syllabus, and you just need to realize the patterns between the number of bonds and the number of lone pairs surrounding the center atom. Remember, the center atom is the atom that basically is bonded to more than 1 atom. It's bonded to at least 2 atoms in the molecule, right? And you also need to remember how to draw these different shapes using the conventions, right? Flat bonds are within the plane of the screen or the sheet of paper. Solid wedges are bonds coming out of the sheet of paper or screen towards you. And the dotted wedges are, or the dashed wedges are actually going into the screen or sheet of paper away from you, right? So that is all about shapes of molecules. If you enjoyed this video, don't forget to like and share it and subscribe to the channel. And inshallah, I'll see you in the next video.